So thanks so much for invitation. This is the title of my talk, Metamaterial Transmission Lines for Wireless Communication, Sensing and RFID. This talk is going to be a more tutorial-oriented talk, okay? Though in some aspects I will not go to the details, okay? I would like first of all also to thank Jordi Naki, Gerard Zamora, Ferran Paredes and Jordi Bonacci of my group who have contributed to this talk. And the outline today is this one. First of all, I will make a brief introduction to the topic of metamaterial transmission lines. And after that, I will show you how to use these artificial transmission lines for the design of some kind of circuits and antennas useful for wireless communications. After that, I will focus the attention on the use of these type of lines for the implementation of microwave sensors based on symmetry-related electromagnetic properties of transmission lines loaded with metamaterial resonators. And to end my talk, I will focus the attention on the design of some kind of chip-based and chipless-based tags for RFID. Okay, so the aim of this talk is to highlight the potential of metamaterial transmission lines, mainly based on splitting resonators and also in other resonators based on them, for the design of microwave components useful for wireless communications, microwave sensors, and tags for RFID. The specific components and devices that will be reviewed today are multiband devices and leaky-wave antennas, which are designed on the basis of dispersion and impedance engineering. Then microwave and contactless sensors based on symmetry properties, and finally chip-based RFID tags and encoders for chipless RFID as well. Well, what are metamaterial transmission lines? Christoph talked about metamaterials transmission lines before a little bit. Let's go again to the detail of these lines. Essentially, a metamaterial transmission line is a host line, microstrip, CPW, etc., loaded with reactive elements, inductors, capacitors, or a combination of them. Thanks to the presence of these reactive elements in the line, we have more degrees of freedom for design as compared to conventional lines. So it means that we have more design flexibility so that we can make device design on the basis of dispersion and impedance engineering. This is the key aspect. Moreover, we can achieve compact size if distributed effects are avoided, so that these lines can be described typically by lumped element circuit models, so that we are in the domain of the semi-lumped planar approach. Okay, what we're talking about, probably for most of you, for sure you, Christoph, are familiar with this line. This is the first composite right left-handed transmission line that was, to my knowledge, that was proposed in 2002 by Professor Calloz and Ito. And essentially, what is this? Well, this is a host line microstrip, in this case, loaded with series capacitors, interdigital capacitors, and shunt-connected inductors. So the unit cell of this line can be described by a model like this one, the model, where in the series branch we have an LC series resonator, and in the shunt branch we have a parallel resonant tank. Okay? So the analysis of the dispersion of this structure gives this result, where ZS is the series impedance and ZP is the shunt impedance, and this is the characteristic impedance. Okay, so the key point here is that this structure does not present a conventional dispersion, but it presents a dispersion of this type shown here, where you have a region, a band, where the phase velocity and the growth velocity are antiparallel, okay? So that wave propagation here is backward or left-handed, and a band where the phase velocity and the growth velocity are parallel, and where the wave propagation is forward or right-handed. Typically, in between those bands, there is a gap. But this gap can be collapsed if the balance condition is achieved, namely, if the series resonance and the shunt resonance are the same. Under this condition, there is a continuous transition between the left-handed band and the right-handed band. And the characteristic impedance varies very smoothly in the vicinity of the transition frequency. Okay. Now, why the term metamaterial transmission line? where the reason is that the line parameters, the phase constant, and the characteristic impedance can be controlled, mimicking the control of the constitutive parameters, epsilon and mu, in metamaterials, okay? And also, a genuine property of some metamaterials, namely backward wave of left-handed propagation, can be also achieved in composite right-handed transmission lines, as I have just mentioned. Indeed, the nature of propagation, forward or backward, depends on the sign of the series reactance and the shunt susceptance. Okay, if we have into account that 10-wave propagation in transmission lines and plane wave propagation in homogeneous and isotropic media is described by the same equation, there is a mapping between the constitutive parameters of the material and the series impedance per unit length and the shunt admittance per unit length of the model of the transmission line, okay? So that according to this mapping, there is this parallelism between metamaterials and transmission lines. So, essentially, if the materials parameters are positive, we have wave propagation which is conventional or forward, okay? If only one of these parameters is negative, the structure is opaque. But if both are negative, then transmission is allowed, but with backward wave or left-handed wave propagation. The phase constant is negative, okay, rather than positive. Similarly, if I have a transmission line, conventional one, which is described with this model, because the series reactance and the susceptance are both positive, propagation here is forward, as you know, in a conventional transmission line. However, if we interchange the roles of the capacitor and inductance in the model of the unit cell as shown here, then wave propagation is backward because the series impedance and the susceptance are both simultaneously negative, okay? So this is the parallelism between metamaterials and metamaterials transmission lines or meta lines from now on. However, there are other composite right left-handed models. For instance, the dual composite right left-handed transmission line, where we have in the series branch a parallel resonant tank and a series resonator in the shunt branch. In that case, wave propagation, wave dispersion is like shown here. First, at low frequencies, we have a forward band, and at higher frequencies, we have a backward band and a gap in between, okay? This is another model, which is the Drude-Lorentz model, exhibiting 3 bands rather than 2, and this is the extended CRLH model, where we have 4 elements in the series branch and 4 elements in the shunt branch, and in that case, we have 4 bands, left-handed, right-handed, left-handed, right-handed, alternating, okay? So we have more flexibility as the number of reactive parameters in the series and in the shunt branch of the T or the P model increases, okay? Finally, this is a generalized model where the number of bands can be made arbitrary just by increasing the number of elements, as I have just mentioned. Okay, let's now focus on the resonant-type approach of metamaterial transmission lines. In that case, the host line, is loaded with electrically small resonators, electrically small in order to have effective parameters, okay? And these resonators can be typically split ring resonators, complementary split ring resonators, and the open counterpass, okay? Probably most of you are familiar with these resonant elements. The SRR can be excited typically by a magnetic, time-varying magnetic field, okay? And this structure can be modeled by this circuit, okay, which exhibits an inductance and the 2 capacitance here, which are the series connection of the capacitance of the upper and lower halves of the structure, okay. By applying duality, we obtain the complementary version of the SRR, the complementary splitting resonator, okay. In that case, the structure can be excited by means of an axial time-varying electric field rather than magnetic field, and again, this structure can be modeled by a resonator like this. Basically, if these structures are etched in the same substrate, okay, they exhibit roughly the same resonant frequency. Okay, now let's go to the open counterparts. The idea is put one ring on the other and open, like a hook shape, like a pair of hooks, like shown here, and open it, so that we have 2 ports for excitation. It means that this structure can be also excited by means of current or voltage sources, okay? This is the open splitting resonator. One important point is that the fundamental resonance of this particle is half the resonance frequencies of this one. So it means that this particle is electrically smaller than this one by a factor of 2. And the reason is the fact that the capacitance of these structures is essentially the edge capacitance of the whole circumference. So it means that it is 4 times larger than the capacitance of the SRR, and hence the resonance frequency is half. Similarly, we can obtain the open complementary splitting resonator from this topology, or applying duality or complementarity to this topology as shown here. And in that case, the ports for excitation are here and here, okay? Again, this structure is, or this resonator is smaller than this one, again by a factor of 2. And the reason in that case is that the inductance is 4 times larger than the inductance of this particle. The model in both cases of the open particles is a series resonator and a parallel resonator, but an open resonator, okay? Okay, let's show you, let us now review some examples of these resonant-type metamaterial transmission lines. This is the first one that was proposed by us in collaboration with the groups of Professor Sorolla in Navarra and Ricardo Marquez in the University of Sevilla. This is a host line, a CPW in that case, loaded with series shunt-connected inductors and splitting resonators, pairs of splitting resonators in the backside. This structure indeed mimics the first metamaterial structure that was presented by David Smith in 2000. And the model of this structure is shown here. Essentially, the C and the L models the parameters of the line. The shunt-connected inductance is shown here. The resonators are modeled by these resonant tanks shown here, and the coupling between the line and the resonators is inductive, okay, is magnetic, as shown here. After some manipulation, this model can be transformed to this one, and this is very similar to the P model of the canonical composite right-handed transmission line. The main difference is the fact that here, this inductor provides a transmission 0. This is the single difference, which this could be good or not, depends. But we have a transmission 0 before the first band, which is left-handed. And here is the version based on complementary splitting resonators. In this case, we have a microstrip line with gaps etched here, as I show you. And here we have in the backside the complementary splitting resonators. And this is the model of the unit cell, where L and CL model the parameters of the line. This P network models the series gaps, and this models the CSRR. This model can be easily transformed to this one through these transformation equations. And again, this is very similar to the P model of a composite right-handed transmission line. The main difference being the fact that we have here a capacitor, which again provides a transmission 0. So these structures exhibit a transmission like this, or like this, okay, with a transmission 0, as can be seen here, and here this is S21, okay. This is the left-handed band, and due to the characteristics of this topology and this topology, the right-handed band occurs at higher frequencies, which are out of the range of the figure. Notice, however, that if I skip the series gap in this case, okay, or the shunt inductors in this case, then what we obtain is a switch of the transmission. Now we have a stop band, okay? You have a notch, essentially you have a notch. We have a notch provided we have only one element, okay? The notch is shown here and here, okay? And if we have an array of this structure, this stop band functionality can be interpreted as due to the fact that this structure is an epsilon negative structure and this structure is a mu negative structure, okay? But of course it can be also interpreted, this behavior, from the point of view of circuit theory. Okay, let us now move to the open counterparts, open splitting resonators and open complementary splitting resonators. Is it possible to implement composite right-handed lines by means of these particles? And the answer is, of course, yes. Well, the reason is that, okay, if we think on the canonical model of a CRLH line like this, shown before, we can synthesize these series resonators by means of an OSRR and the shunt resonator, parallel resonator, by means of an open complementary split resonator, as shown here. So we can implement this, for instance, in CPW technology, as shown here. These are the OCSRRs. Okay, we put a pair in order to avoid as much as possible the slowed mode. Okay, and here we have one OSRR here and one OSRR here. Okay, we can also think, of course, in a pi configuration, as shown here. Okay, providing a similar topology but in a pi configuration. Okay, now. We can implement balance composite right-handed OSRR and OCSRR loaded lines, as can be seen in this structure, in this diagram, this dispersion diagram. This is a balance structure with the left-handed band and the right-handed band corresponding to this topology. And here I show you the transmission S21 and S11. Okay, and this can be done in spite of the fact that there are parasitics in this structure, and these parasitics are essentially these capacitors here and these inductance here, and are due to the fact that there is always some phase shift in the unit cell of these lines. However, these parasitics are not very important, and in any way, we cannot say that these parasitics provide more degrees of freedom, because it is very difficult to control the parasitics, okay? But the fact that the parasitics are present does not mean that we cannot achieve CRLH characteristics with a continuous transition between the left-handed and the right-handed band corresponding to the balance conditions. We can do that. Okay. Now, sometimes the design of metamaterial-based structures, rather than on dispersion and impedance engineering, it is based on a resonance phenomenon. Okay, in that case, maybe we can talk about these lines as transmission lines with metamaterial loading, in the sense that these lines are loaded with electrically small resonators that are useful for the implementation of metamaterials. Okay, and these transmission lines with metamaterial loading can be applied to the implementation of some kind of sensors, as will be shown in a few minutes, multiband antennas, radio frequency barcodes, etc. Okay? Other possible resonant elements that are useful in this type of lines are the folded step impedance resonator. It is very similar, the behavior of this structure is very similar to the one of the SRR. Okay? It can be excited typically by a magnetic field, but also by means of an electric field in this direction, because there is an electric wall here, and there is an electric dipole in this direction. Another interesting particle that will be used later in this presentation is the so-called electric ELC resonator. It is essentially a pair of C-loaded loops, okay, one here and the other here, okay. There is, for the fundamental resonance, there is an electric dipole in this direction, so this particle can be excited by means of a uniform electric field in this direction, as shown here, but it cannot be excited by uniform magnetic field in the axial direction, and at the fundamental resonance. And the reason is that at the fundamental resonance, the currents in each loop are opposite. One is clockwise and the other one is counterclockwise, okay? But it can be excited by means of counter-magnetic fields, as shown here. So this is a very interesting particle, as will be seen later. And finally, this is another one, a structure that can be used is the spiral resonator. The advantage in that case is that this particle is electrically very small. Okay, these are kind of particles that can be used. Okay, let's now move to the two examples I mentioned before of application of this type of structures. One is multiband devices, and the other one is Leaky-wave antennas. Okay. Let's focus now on multiband structures based on impedance inverters. So we are talking about the implementation of dual band or multiband in general impedance inverters. So we can take benefit of the controllability of the dispersion in composite right-handed lines for the implementation of multiband microwave circuits based on multiband impedance inverters. That's the key idea. Inverters that exhibit a phase of 90 degrees at the operating frequency. So we must achieve this phase shift at several frequencies. Okay. So the point is that to achieve N-band functionality, we need in general at least n reactive elements in both the series and shunt branches of the T or P model of the line. So it means that we need 2n elements, okay? If we denote the characteristic impedance of the inverter as ZA, the 2n equations necessary to univocally determine the circuit elements of the line are given by these expressions. These expressions comes by forcing the phase shift and the characteristic impedance to be plus or minus 90 degrees at the operating frequencies, okay? And in this equation, n represents the frequency index, and Cs and Cp, the reactances of the series and shunt branch of the circuit model. Okay. Now, let's going to focus on the implementation of dual band impedance inverters based on OSRR and CRLH loaded lines. This is the model of the unit cell, including the parasitics. So this is not a P model, not a T model, and the number of elements, rather than 4, as needed at least for a dual band device, is 6. But the fact that we have 6 models is not a problem. We have more degrees of flexibility, but be careful, because the parasitics, we cannot have a real control on the parasitics. Anyway, we can obtain the series impedance and the shunt impedance of the equivalent T-circuit model, okay? And from these values, we can determine the elements in order to achieve the dual band functionality. I'm not going to enter into the details, okay? You can go to our papers if you want. I just show here you some examples. For instance, a dual band power divider, operative at these frequencies, okay? The idea is to implement an inverter with this impedance, okay? This is the inverter, okay? Here is the dispersion characteristics of the inverter and the characteristic impedance, okay? And at the design frequencies, the values of minus or 90 degree phase shift and this impedance are obtained, okay? And if you add 2 output access lines to the impedance inverter, then we obtain the dual band power divider, shown here, exhibiting the functionality, okay? This is the matching of the divider at the design frequencies, okay? This is just one example. Another one is a quad band component, in this case a quad band junction power divider, Y-junction power divider, based on the extended composite right-handed transmission line model, okay? Remember, in that model we have 4 parameters in the series branch and 4 parameters in the shunt branch. So it means that we can achieve a quad band functionality as it is. This is the topology of the divider, the fabricated prototype, and here the matching power division, where you can see the 4 bands of the quad band divider, which has been designed to operate at these 4 frequencies. Another possibility, I will skip this slide for time constraints, is a quad band branch line hybrid coupler. This is the topology and the results of the characterization of this quad band device. Okay. Now, another possibility already raised by my colleague Christoph Kaloth is the possibility of using this composite right-handed structure for the implementation of leaky-wave antennas. So these leaky-wave antennas, based on composite right-handed lines, are quasi-uniform antennas that radiate from the fundamental mode, which is important, and allow for continuous scanning from backward to forward direction. Okay, so this is again the dispersion diagram of a typical composite right-handed line. Okay, now if we denote by k the wave number of the leaky mode, okay, being beta the phase constant, if the phase constant is larger than the free space wave number, then the mode is a guided one. Okay, but if beta is smaller than k0 but positive, then we have a leaky mode, okay? We are in this region, which is forward. And if the beta is negative, but the absolute value is smaller than the wave number in free space, then the mode is leaky, but it is backward. This corresponds to this region here. And this expression gives the angle of the radiated beam where from it can be seen that here we have roadside radiation, forward and backward radiation. Okay, so there are many examples of Leaky-wave antennas based on composite right-hand structure in the literature. One possibility, for instance, is to use this kind of resonant elements, again, splitting resonators. And in 2007, in collaboration with Mario Sorolla and his group, we do implement a Leaky-wave antenna based on a CPW structure loaded with splitting resonators. The problem is that there is an important far-field cancellation due to the anti-parallel magnetic currents in the slots of the CPW. And by truncating the symmetry, you can improve the radiation efficiency of the antenna. And it was done in 2007 by skipping just one row of splitting resonators on top of one of the slots. And another possibility is to cut the CPW by the middle, and then we convert the CPW essentially in a slot line. And this is the kind of antenna I show you here, based on a slot line with a splitting resonator. Okay? We have calculated the number of sections of this structure so that we achieve 90% of power radiated in the structure. Once we have calculated the dependence of the attenuation constants with the number of unit cells. This is the structure, the dispersion of the structure, when you can see the balance condition is achieved. And here I show you some results of the characterization of this Leaky-wave antenna. This is the gain, okay, and the scanning angle as a function of the frequency. This is the radiation pattern simulated and measured, okay, and this is the orthogonal radiation pattern. Important point is that even though it is not shown here, but the radiation here is specular due to the fact that we don't have a ground plane in this antenna. Okay, let's now move to the field of sensors based on symmetry properties. Okay, the idea is to load transmission lines, microstrip, differential microstrip, CPW, etc., with symmetric or even bisymmetric resonant elements, typically useful for implementation of metamaterials. Okay, what's the principle of this sensing approach? This is the important point. Well, the idea is that by loading the lines with symmetric resonators, the transmission characteristics of the lines can be controlled through the relative orientation between the resonators and the line. That's the key point. So we can distinguish among two different situations. The first one is the non-symmetric one, corresponding to symmetry planes of the line and resonator not aligned. Typically, in this case, a transmission notch appears at the fundamental resonance frequency of the resonant element. And the other situation is the symmetric one, where the symmetry planes of the line and the resonator are perfectly aligned. A notch, in that case, a notch may appear or not, depending on the electromagnetic nature, electric wall or magnetic wall of the symmetry plane of the line and the resonators. Let's consider a case example to understand this, what I'm talking about. Let's consider a CPW loaded with a splitting resonator. This is the CPW, where in the symmetry plane we have a magnetic wall for the fundamental CPU mode, okay, even mode, of course. This is the electric field distribution in the cross-section of the structure. And the SRR shown here in a square topology or round shape, it doesn't matter, exhibits an electric wall at the fundamental resonance frequency in the symmetry plane. Okay. Now, let's consider that we have a single splitting resonator etched in the backside of the CPW, okay, in symmetric configuration as shown here. Here we have a magnetic wall for the fundamental mode of the CPW, but an electric wall for the fundamental resonance frequency of the SRR. Under these conditions, okay, there is not a net axial magnetic field able to excite the particle, and the structure is transparent. Even though we perfectly know that if rather than one, we have a pair of splitting resonators, each one on top of each slot, then we have a notch. But not if we have only one symmetrically oriented. Okay. However, The line inhibits signal propagation at the fundamental resonance for the slowed mode, because for that mode, of course, we have an electric wall in the symmetry plane, so that if this wall and this wall are of the same electromagnetic nature as is the case, then the structure is opaque and a notch appears at the fundamental resonance frequency of the SRR. So for a symmetric structure, the line is transparent if the symmetry plane of the line and resonator are of different electromagnetic nature. And the line exhibits a notch at the fundamental resonance if the symmetry plane of the line and the resonator are of the same electromagnetic nature. Here is the verification. Notice that for the fundamental mode, even mode, the structure is transparent here, okay? But the notch appears in transmission for the odd mode, okay? And in this case, the simulation shows us that for this configuration, symmetric one, there is total transmission, but this total transmission is lost if I rotate a little bit, 10 degrees in this case, or if I laterally shift up or down this resonator, in this case by 5 millimeters, okay? We have a strong notch. Another interesting particle, as I mentioned before, is the LC resonator, okay? In this case, if we load the CPW with this resonator, we have two extreme situations. This is the 0 degree situation and the 90 degree situation. For this resonant particle, okay, there is an electric wall for the fundamental resonance here. So it means that for the fundamental mode of the CPW, we have walls of different electromagnetic nature, and in that case, the structure is transparent, okay? But if we rotate 90 degrees, we have here a magnetic wall for the resonator. So we have walls of the same electromagnetic nature, meaning that we have a strong notch for this 90 degree situation, as shown here. Okay, so this can be applied, for instance, this type of structure, for the implementation of many types of sensors based on disruption of symmetry, on truncation of symmetry. And the good point in these sensors is that because symmetry is not dependent on variation in ambient conditions, these sensors could be more robust in front of changes in environmental conditions. That's the good point of these sensors, okay? These sensors can be, these structures can be applied to spatial sensors, to sensors for the electric characterization, etc. Okay, and here I show you an example of a rotation sensor. Okay, where the spatial variable is the angle, the dynamic range is this one, and the output electrical variable is the magnitude of the notch in S21 at the resonant frequency of the resonator. Okay, try to go fast. And then here I show you the idea of the structure. This is a CPW loaded with a circular shaped ELC resonator. Okay. So here the idea that the reason for this circular shape formed for the CPW and the resonator is that the linearity is much better. Okay. So let's go to see the experimental setup. Essentially, this is the CPW, okay, and we put the resonator in a cylinder made of Teflon, which is attached to an stem motor that can make it rotate, okay. And here I show you how by varying the rotation angle, okay, the notch increases almost linearly, okay. And this rotation sensor can be applied to the implementation of an angular velocity sensor. The idea is very simple. Essentially, we have the CPW structure and the rotating element on top of it. So if we inject here a carrier signal tuned at the fundamental frequency of this resonator, the rotation of this resonator modulates the amplitude of the signal. It is essentially a frequency, an amplitude modulator system, okay? So that by means of an envelope detector, we can obtain the envelope, and from the distance between adjacent peaks, we can determine the rotation speed. Well, this is the idea, and here I show the results. This is the experimental setup. where we have a signal generator, the step motor, and an oscilloscope in order to obtain the signal. And here is the isolator needed to avoid, or the circulator needed to avoid unwanted reflections, and the envelope detector. And from this distance, we can determine the velocity. Okay, and to end the talk very briefly, the final part is dedicated to chip and chipless-based tags. Okay, here I show you two examples. One is the implementation of dual-band chip-based tags for ultra-high frequency RFID. Okay, the dual-band functionality here refers within the regulated UHF subbands, which can be achieved by loading an ordinary tag with metamaterial resonators. So the idea is very simple. Take into account that in UHF band, the regulated frequencies worldwide are very close. For instance, in Europe, this is the frequency, and this is the frequency in USA. Okay, so the idea is to implement a tag functional, a dual band tag functional at these frequencies. How to do that? Well, in order to obtain a good read range, it is convenient to achieve conjugate matching between the antenna and the chip, as is well known. So the idea here is, okay, let's consider as an example a slot antenna like this one. This slot antenna exhibits an impedance, an input impedance with the resistance and the reactance. Okay, so the idea is to apply a perturbation method, where we essentially implement the matching network by means of a transmission line. Okay, so we can calculate the characteristics of the line, phase phase constant, and characteristic impedance to obtain conjugate matching at the central frequency between the frequencies of the two subbands. Okay, this can be easily achieved. Okay, and then we perturbate the line by coupling and a splitting resonator. This coupling modifies the phase and the characteristic impedance of the line so that we can achieve conjugate matching at the two frequencies. Okay, I cannot explain the details, this is too long, but this is the main idea, perturbation method. This works as shown here. We have a good matching. This is the matching network, this is the chip, and this is the slot antenna. But the key point is that we can avoid the matching network because we can directly apply these loading resonators directly to the antenna. For instance, a typical antenna like a meander line antenna. So this is the conventional tag, this is the dual band tag, where we skip the matching network because we obtain this, we apply this perturbation method directly to the impedance of the antenna. Okay, here I show you the results. This is the single band tag, okay, and this is the dual band tag, red range, okay, showing that we obtain a good read range at the European and USA frequency. Or it can be also applied to a folded dipole antenna, the same idea, okay. And to end, just let me show you that another possibility to reduce the cost of tags is to implement chipless-based radio frequency identification tags. And this can be implemented in time domain, in frequency domain. For instance, in the case of the frequency domain, we can implement chipless RFID tags similar to optical barcodes, but operating at radio frequency or microwaves. Okay? The idea is to load a transmission line with multiple resonators, each tuned at a different frequency. Okay? So that the presence of a 1 or a 0 is the presence or not of the resonator. Okay? So that's the idea. This is for me the top record of these barcodes, which is due to Professor Chandra Karmakar and his group with a 35-bit chipless tag, which is the top record in the world to my knowledge. Okay. Another point is that I'm not sure that from a practical point of view this works or not. Okay. This corresponds to the all ones, okay, for the 35 bits. And our idea, where these are only preliminary results, is to implement barcodes based on symmetric resonators. And the idea is to take benefit of the orientation of the resonator in order to achieve or to control the notch level and to try to achieve more than one state, more than two states by means of a single resonator. Okay? So the idea is to consider the possibility of implementing multiple states per resonator, and even the possibility to implement reconfigurable radio frequency barcodes and wireless sensors with identification. And here ends my talk. Thank you very much.